Welcome to ASU's University Academic Success Programs. This video will cover the topic, work and energy.
Work? I shouldn't have to worry about work yet. I'm a college student.
The work described in this video is a different kind of work. In physics, work occurs when a force is exerted on an object, causing a displacement, and it is measured in the standard unit of joule, which is equivalent to 1 Newton meter. The work equation looks like this. Work equals force times displacement times cosine of theta.
Why is there a cosine of theta being multiplied in this equation?
Good question. The theta in this equation is the angle between the force vector and the displacement vector. Because force and displacement are vectors, we are finding the dot product of them, and to find the magnitude of the dot product, we multiply the magnitudes of the two vectors and the cosine of the angle between them all together. So when calculating work, it is important to identify the angle between the force being exerted and the direction in which the displacement is occurring. Let's say that I'm applying a force onto a box at a 30-degree angle to the horizontal, and that a displacement is occurring in the horizontal direction. The work in this scenario would be calculated by multiplying the magnitude of the force, the total displacement of the box in the horizontal direction, and the cosine of 30 degrees.
Oh, okay. This seems to all make sense. What does work have to do with energy, though?
Before we begin to get into the relationship between work and energy, let's go over the different types of energy. The two types of mechanical energies are kinetic and potential energy. Potential energy refers to the stored energy caused by the position of an object. If there is a ball sitting on top of a hill, even though it is not moving, it has potential energy. The potential energy of an object can be found by using this equation. Potential energy, PE, equals mass times acceleration due to gravity times the height from the ground. We multiply the mass of the object, the acceleration due to gravity, and the vertical position of this object. The ball's elevated position causes it to have stored energy that could be released if, say, the ball began to roll down the hill. Going back to the example of the ball on the hill allows us to better understand the second kind of mechanical energy, kinetic energy. Kinetic energy is energy of motion like the ball rolling down the hill. And it can be found by using this equation. Ke, kinetic energy, equals 1/2 times mass times velocity squared. The potential energy of the ball is converted to kinetic energy when it begins to roll down the hill. An object that possesses mechanical energy has the ability to do work. A very important principle in physics is the work energy principle, which states that the work done on an object by a net force equals the change in kinetic energy of the object. This principle is modeled by this equation. W equals delta Ke, or work equals the change in kinetic energy. Let's try out a problem involving work and energy. In this problem, Justin is driving down a road at 32.8 meters per second in his 1,510 kilogram car. He spots a police car with a radar gun and quickly slows down to 20.1 meters per second. We are asked to determine the initial kinetic energy of the car, the final kinetic energy of the car, and the amount of work done on the car during the deceleration. For the first part of the problem, we will be using the formula for kinetic energy that we defined earlier. Ke equals 1/2 mv squared. We will use the mass of the car given in the problem and the car's initial velocity to calculate the kinetic energy. Doing so, we find that the initial kinetic energy of the car is 812,259.2 joules. Now for the second part of the problem, we will be using the same equation as the first part of the problem, but we will be using the velocity of the car after it decelerated, 20.1 meters per second. Doing so, we find that the final kinetic energy of the car is 305,027 joules. For the last part of the problem, we will be using the work energy theorem, which states that the work done on an object is equal to the change in kinetic energy. Knowing this, we will subtract the initial kinetic energy from the final kinetic energy of the car. In doing so, we find that the total work done on the car is negative 507,232 joules.
Oh, okay. I think I understand what is going on, but just to be sure, let me go over what I've learned. Work is done on an object when a force exerted on it creates a displacement. It can also be found by finding the change in kinetic energy of an object.
That all sounded right. Now, with just a little more practice, this topic can be mastered.